Dr. Chan, can you hear me?
Yep, I can hear you.
Very nice. Thank you, sir.
Yep. All right, it's 7 o'clock. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good. I had a Super Bowl watch party over the weekend, although most of my friends aren't really into football. And so I was texting all my friends last week, kind of, asked if they want to come over. And they all kind of said the same thing. And so they said, I'll come and watch Rihanna and I'll come and eat your food, but then I'm not really interested in football. And so I was like, all right, at least I'll have some company watching the game. So, that was good. So I cooked a ton of food for my friends. They ate it. They watched Rihanna. And then no one was really interested in the game. But that was okay. I got to enjoy the game. The game itself was very good. So that was good. Okay. All right. So today,
Dr. Chan, I have a question.
Sure. Yes.
Were you rooting for a individual team or?
Not really. I like both teams, and so I was just happy it was a good game. The ending was kind of a little bit kind of weird, but up until that point, it was a good game. So yeah, I was happy overall.
Very nice.
All right, so today, we're going to be talking about boundary conditions. And so this is kind of the continuation of what I consider to be like the FEA basics part of the course, right? And so before we did activity 2 last week on Monday, we talked about meshing. And so I'd say meshing is kind of the first of the basics. And so we talked about, what meshing was, what are your options in terms of meshing, and kind of what are some of the basic metrics, what are some of the basic features you have, okay? Today, we're going to talk about boundary conditions, which is the next part, which is all the loads and constraints. Okay. So I know, we've done a couple activities at this point, and so, I know, probably everyone has an idea of what the boundary conditions are. But I wanted to have this lecture just so, we have kind of an exact definition of what the boundary conditions are, what purpose they serve, and kind of what are some kind of practical tips in applying boundary conditions. Okay. All right. I think that's all my announcements. Are there any questions I can answer before we get started for today? Yeah. Midterm project will be announced after activity 3. And so for the first 3 activities, I consider those to be kind of introduction to ANSYS. So once we're done with activity 3 is assemblies basically. So how do we work with multiple parts? Once we're done with activity 3, then I think you guys are ready to start working on the project. So probably by the end of next week, if not the early of the next week after that, I'll talk about the midterm project. Yeah. All right. Any other questions before we get started for today? All right. So let's talk about boundary conditions. All right. So kind of, the reason I do boundary conditions second is that, sequentially after the meshing, you have to apply the boundary conditions. Okay. So boundary conditions is not an idea that's unique to FEA. You've probably heard the term boundary conditions in, hopefully you've heard about it in at least a couple other of your classes, especially your math classes. Okay. And so the reason we need boundary conditions in general is we need them to kind of fully specify the solution to a differential equation. Okay. And if you recall, FEA, at its core, FEA is really just a different way to solve differential equations. Okay. And so if we're solving differential equations, it really doesn't matter, what method that we use. We're going to need boundary conditions at some point in the process in order to fully specify our solution. Okay. And so let me do just a very quick example with the 1D case, just so I can illustrate kind of what's needed. Okay. And so this is one that we can solve by hand. So you'd probably never solve an equation like this with FEA, unless you were kind of just learning the basics of FEA. But it's good to kind of illustrate why we need boundary conditions in the first place. Okay. And so we have this a very simple differential equation. So we have d squared u dx squared is equal to 3x squared. Okay. So let's go ahead and solve this equation for u. Right. And luckily for this equation right here, we can just solve for u by just simply integrating. And so if we integrate once, side, we end up with du dx. On the right-hand side, we take the integral of this, we get x cubed. Okay. But, since we're doing indefinite integrals, we know that whenever we perform indefinite integrals, we have to add an arbitrary constant. Okay. Spell today. Okay. And so it doesn't matter, I picked this differential equation just so that we can solve it quickly. But no matter if you're solving it with, the characteristic equation, or, whatever your favorite ODE solving method is, you're going to end up with an arbitrary constant. Okay? All right, so let's integrate again. And once again, it is an indefinite integral. Okay. And so if we integrate again, we get u of x is equal to integral of x cubed is 1/4 x to the 4th plus c1x plus c2. This right here is our general solution. All right, so the reason we call this the general solution is that, technically this equation right here is a solution to the differential equation, right? So we take this as it is, and so even with the arbitrary constants, if we plug it back into this equation, it's going to satisfy the equation, right? And so it doesn't really matter what the values of c are. So they could be, 1, -50, 9,001, okay? It's going to satisfy the equation, but they're only arbitrary up to the constant, right? And so in order to get a full solution, in order to get a solution with the constant specified, we need the boundary conditions. You can almost think of the boundary conditions as extra equations that we're adding to our system in order to solve for those constants. Okay. So I'm just going to use kind of arbitrary boundary conditions here. And so our first boundary condition, let's say we have u of 0 is equal to 18. Okay. So we have a direct specification on the solution value. Okay. And then our other boundary condition will say du dx at x is equal to 10. We'll say this is equal to -5. Right. And so what these two boundary conditions give us is that they give us two extra equations that we can use to solve for C1, C2. Okay. So let's apply them. So let's start with the first boundary condition. So u of 0 is equal to 18. Okay. And so if we take our solution for u, we plug in 0, what we get is 1/4, 0 to the 4th, plus C1 times 0, plus C2. That's equal to 18. Okay. Of course, every term with the 0 is just going to be 0. And so what that simply gives us is that C2 is equal to 18. So our other boundary condition, of course, is du dx at x is equal to 10 is equal to -5. So first, let's take du dx. So du dx in this case is x cubed plus C1. So let's plug in x is equal to 10 here. So we plug in x equal to 10, we get 10 cubed plus C1. This is going to equal to minus 5. We solve for C1. We're going to subtract 10 cubed from both sides. So 10 cubed is 1,000. Okay. And so we end up with minus 1,005. Okay. All right. And so if we plug both of these in, what we get is u of x is equal to 1/4 x to the 4th minus 1,005 x plus 18. And this is what I like to call the full solution, because all the arbitrary constants have been specified. Okay? So not only is this equation here, is it going to satisfy the original differential equation, but it's also going to satisfy our two boundary conditions as well. Okay? All right. So that was a very simple case. And so, the only reason I bring that up is just to say that whenever you have a differential equation, you need boundary conditions in order to fully specify the solution. So FEA is exactly the same. Okay. Okay. And so in FEA, you need boundary conditions in order to have a valid solution, a valid simulation. In fact, and you may have tried this already in the first two activities, if you try to run a simulation without applying boundary conditions, ANSYS is actually going to give you an error, because what they've been telling you is that the problem is not fully defined, or it's not fully constrained. Okay. Okay. And that's just purely from a mathematical point of view. Okay. And so just purely, if you're just purely looking at the mathematics, you just can't solve a differential equation without boundary conditions. Okay. Right. But when we're doing, what I call practical FEA, which is kind of what this class is all about, applying FEA to analyze physical systems, I think when we think about boundary conditions, they take a slightly different interpretation. And so for practical FEA, when you think about boundary conditions, those we like to often think of those as what I call constraints and loads, or loads constraints.
Dr. Chan, I have a question, sir.
Yes, sir.
So let's say we have a simulation, and let's say we use a set of boundary conditions for that specified simulation, and I'm talking about FEA.
Yep.
Is it possible, and we get our result using that simulation and that first set of boundary conditions, is it possible to get the same results using that same simulation but a different set of boundary conditions?
It's possible. There's not a unique relationship between a particular set of boundary conditions and a particular result. And so you can get the same result using a different combination of boundary conditions. It's just kind of how you apply them. And so, for instance, kind of the very simplest one that you can think of is that, let's say that you're applying your load and you apply it as a force, right? So that's kind of what we did in activity 2. Yeah. So you apply like a 100-pound force in a certain direction. You can obtain the same results if you change that force to a pressure load instead, right? And so if you compute the pressure such that
I see.
Yeah, so if you compute the pressure such that it applies the exact same amount of load as the force, you get the exact same result. Exactly. Yeah.
Thank you, sir.
Mm-hmm. Yeah. So our boundary conditions, that's I think physically what we like to think of them as our loads constraints. Another way that you can think of them is that you can think of them as any kind of external factors things that aren't explicitly in the CAD model or not explicitly in the simulation that are having an effect on your physical geometry. And so, for example, if we think of activity 2, we did a simulation of a bike crank. Okay? And so our CAD model consisted of just the crank geometry, which is essentially just a rod. Okay? When we applied our boundary conditions, there were two main boundary conditions that we applied. We applied a fixed constraint on one side, and then we applied a force node on the other. Okay? The fixed constraint was meant to model the fact that this crank is attached to a bike frame, right? And so, of course, at least in the activity, we weren't simulating the bike frame itself. And so to include that effect on the simulation, we basically encapsulated that within a boundary condition, okay? And same thing with the force. And so the force is basically the effect of someone's foot, pushing down on the pedal. Okay? We weren't actually modeling the foot itself. We were just kind of modeling the effects of the foot. And so, that was something external to the bike crank, but it is having an effect on its physical response. And so that's why we included it as a boundary condition. And so that's kind of another nice way that you can think about boundary conditions. Okay. Another way that you can think about it So another way to think about boundary conditions is to think of them as like inputs to the system. Okay? Or you can almost think of them as kind of the actors or the instigators in your system. So this last interpretation is kind of interesting, and it's kind of the way a lot of people think about FEA in general. Okay? And so when you have kind of a physical system, you can almost think of the kind of what you observe as the simulation results as that's the system's response to the boundary conditions. Okay? So that's the response to the loads and constraints. Okay? Okay. So I think, we might have touched on this, before in an earlier lecture, but, when you have a physical system just by itself and nothing is really acting on it, it's just chilling most of the time, right? And so let's take that chair, for instance, right? And so there's, presume people, there's a red chair right there, right? So I'm not doing anything to it right now. There's no loads. Well, I mean, the become gravity is the load, but there's no real loads that are being applied onto that chair. And so it's just kind of chilling, okay? And so if I were to apply a boundary condition on the chair, so if I were to walk up to it and just Sparta kick it across the room, then of course it's going to react, right? Because I'm applying a load, a force onto the chair, right? How the chair responds to that, how quickly it moves away, how far it moves, whether it spins or not, that depends on, the properties of the chair itself. And it also depends on the laws of physics, okay? And so you kind of have this kind of way that you kind of view physical systems where, you have these boundary conditions, which are kind of the instigators. They're the ones that are causing the response. And then what actually defines the response or how an object responds is governed by its differential, it's governed by its governing equations as well as its material properties, which we'll talk about on Wednesday. Okay? All right. Any questions on this so far? Okay. All right. So here's kind of so so far all we've really talked about just kind of the motivation of what the boundary conditions are and why we need them. Okay. So let's talk about more practically now. And so when I talk about when I like to talk about boundary conditions in FEA, I like to sort them in two categories. And so there are constraint type boundary conditions and there are load type boundary conditions. And so, the reason I kind of sort them into two categories is that they both kind of have unique kind of effects on the solution itself. And there's kind of unique requirements for both as well. Okay. All right, so let's talk about constraint type boundary conditions first. And so another name for these constraint type boundary conditions is often called Dirichlet boundary conditions. So maybe that might be a term you've heard before in a previous math class. I might say I'm going to try to say constraint type boundary condition because I think that's more consistent with what ANSYS has. But I've been trained to say Dirichlet. So I might say it accidentally. So if I say Dirichlet, what I mean is constraint type. Okay. Okay. And so what are constraint type boundary conditions? So the reason we call them constraint type is because they basically constrain the primary solution variable to have certain values. Okay. Another way you can think of it is that it's forcing a certain value from the primary solution variable. All right, so just a quick example. So, when we're talking about structural simulations, which is what we're going to do for the majority of this class, the primary solution variable is deformation or displacement. Okay. And so, when we apply the most common constraint that we're going to apply in this class is the fixed constraint, okay? Or fixed support, I guess. And so the fixed support boundary condition, what that forces from the solution is that it forces the deformation to be 0 at that location. And so since this is a boundary condition that forces the deformation to be a certain value, in this case, we're forcing it to be 0, then this falls under the category of constraint type boundary conditions. Okay. Another example. And so let's talk about the mathematical example that we did at the beginning of class today. Okay. And so if you look back at that example, we had two boundary conditions there. Okay. I chose those very deliberately so that they refer to the two types of boundary conditions we're going to talk about. Okay. But the first boundary condition that we had, which is z of 0 is equal to 18. Okay. This also is categorized as a constraint type boundary condition. Why is that, right? And so, when we're solving this equation, u here, u is our primary solution variable, right? And so since we're forcing u to have a value of 18 at the origin, then this counts as a constraint type boundary condition. Okay. Yes, sir.
Dr. Chan, I have a question.
Sure.
You mentioned that there's two types of boundary conditions, constraints and loads.
Yes.
What about time? Is there time dependent boundary conditions or no?
Yeah, there are. So we're going to cover unsteady simulations, I believe, in activity 5. We're mostly going to be worried about static conditions first, because unsteady simulations are they're a whole nother can of worms. Honestly, it's and even the one that we are going to do, it's going to be fairly basic, because the theory that goes behind unsteady simulations is pretty vast, and so you kind of need its own. It kind of needs its own class. So we'll introduce the idea, and we'll talk about kind of the basics of how to set it up. But when you start to do unsteady simulations, you also need initial conditions as well. And so we'll talk about all that in activity 5. So I think that's going to be after the midterm project.
Sounds good.
Yep. Mm-hmm. Okay. So why are constraint type boundary conditions important? Well, constraint type boundary conditions are important because you need to have at least one in order to have a valid FEA simulation. You need to have at least one. If you don't have at least one constraint type boundary condition, ANSYS will literally not let you run the simulation at all. Okay. So why is this? Okay. So the reason this is, and I think it's actually easiest to go back to our first mathematical example. Okay. If you look and see what effect the constraint type boundary condition had, it mainly allowed us to specify the value of C2. Okay. And so when we applied our constraint type, that's what gave us our value of C2. Okay. So C2 is in an interesting position here because it's just a constant that we add to the entire solution, right? And so another way that people think of C2 is that this is almost like a reference point for the entire solution. And so by applying a constraint type boundary conditions, you're basically applying a reference point for the whole solution. Okay? Without that constraint type boundary condition, there would be no reference for the entire solution. Okay? And so, let's look at this example again. And let's say that we change this constraint type boundary condition. Let's say we change it to a derivative boundary condition instead. Right? So let's say that we have du dx at x is equal to 0 is equal to 18. Okay? If we change that boundary condition to that, what you'll see is that it's literally going to be impossible to solve for the value of C2. Okay? And so if you have basically two derivative type boundary conditions, there's no way you can solve for this reference point. Okay? And so FEA is the same way. And so basically, in order to have a reference point for the solution, you need to have that constraint type boundary conditions. Okay. And so we can kind of see this physically as well, right? So let's look at a physical situation where we don't have a fixed support. Okay. So let's say we have a beam. Okay. Normally, when you have a beam, you have a pin joint, right? And so let's say that we have one joint here that's pin. Okay. And so this pin right here, this pin is kind of constraining the motion of the beam. So even if we have a roller support on the other side, right? Because we have that pin support and that's acting kind of as our constraint, there's, this beam is not going to, we're not going to have any rigid body motion. Okay. But if we had the same beam, but instead of a pin support on the left, we instead had a roller joint. Okay. We had a roller joint right there, right? So we had two rollers. Let's say that we have a very hungry professor come and just kick the crap out of this. Okay. What's going to happen to this beam, right? Because there's nothing that's fixing it down, it's going to start moving, right? So instead of a beam, you have a skateboard. Right. So this is kind of the physical intuition. So, I think, when you talk about constraint or, boundary conditions in general, it's very easy to kind of get caught in the mathematics and the mathematical jargon and all that stuff. But, there's kind of a very a lot of times there's kind of a very simple kind of physical reason why we need things a certain way. And this is kind of that reason. Okay. All right. Any questions on this? Okay. All right, so that's constraint type boundary conditions. I'll leave a quick note here because I know people have asked about other types of FEA. So I know this class just naturally has kind of a lean towards structural dynamics. Okay, but if you want to do an FEA simulation on thermal heat transfer analysis or fluids, the rules are kind of the same. It's just what we define as a constraint type boundary condition is different. Okay? So for thermal simulations. For thermal simulations, traditionally the constraint type boundary condition is a temperature boundary condition. Okay. And for fluids, the constraint type boundary condition is usually either velocity or its flow rate. For thermal, it gets a little bit more complicated because you can also have either a convection type boundary condition or radiation. Those technically count as constraint type boundary conditions, but kind of in the most basic sense, kind of what's usually applied is just a straight up temperature boundary condition. Okay. And for fluids, you need to have at least one velocity or flow rate boundary condition. Usually that takes the form of a no slip boundary condition, but you need to have at least one in your fluid simulation for the same reason. Okay, all right, so that's the first type of boundary condition, constraint type. Let's talk about the next one, which is load type boundary conditions. Okay, so load type boundary conditions, another name that you'll hear from them a lot is called Neumann boundary conditions. Don't ask me who Dirichlet and Neumann are. I still don't know. It's one of my biggest pet peeves about just science in general is that we name equations and we name important stuff after the people that discover them, which is cool, I guess. That's their legacy. But then if you just someone says, give me the Bernoulli equation, you have no idea like what the hell that actually is because it's named after the dude, not after what it's actually doing, right? So I love equations like the heat equation because the heat equation just tells you right away this is an equation that governs heat. But you say what's a Neumann boundary condition? You have no idea because you have no idea who that guy was. So I feel like I have to rant about this every semester because it always annoys me. But I have to do it. Okay, all right. So what are load type boundary conditions? So load type boundary conditions, specifically speaking, they're usually boundary conditions that involve a derivative of some kind. Okay. But for practical FEA sense, I like to think of load type boundary conditions as kind of almost everything else that's not a constraint type. Okay. So basically any external effect that does not count as a constraint type boundary condition, that's not kind of directly constraining the solution variable, we call that a Neumann. Okay. So another way that you can think of it is that, Neumann boundary conditions, of course, is going to have an effect on the primary solution variable. Okay. You apply a pressure, you apply a force on a physical system, it's going to affect its deformation, but it doesn't do so in a direct way. It kind of does so in kind of an indirect way, where you have to apply it to the governing equations as well. Okay. Because if you look at the constraint type boundary conditions, it didn't really matter what the governing equations were for that, right? And so if you look back at our example, right, it didn't matter what our differential equation was. Our constraint type boundary condition said that u of 0 is equal to 18. It doesn't matter what u looks like. It doesn't matter what its governing equation looks like. It just says that u has to equal 18 here. Okay, so constraint types don't really care what the governing equation is. For Neumann type boundary conditions, usually the effect that it has, you have to go through the governing equations in some way. Okay. All right. And so, for example, in our activities so far, our load type boundary conditions have been like a force or if they've been a pressure. And so force and pressure, you apply force onto a system that's fixed in space, of course, it's going to affect the deformation of the system. It's going to cause a deformation. But the amount of deformation that it causes, it depends on the governing equations. It depends on how stiff the system is. It depends on the actual governing differential equation. So of course, another example for this from our first mathematical one was our derivative condition. Okay, so I believe was du dx at x is equal to 10 equal to -5. Okay. So we classify this as a Neumann type boundary condition because it involves a derivative. Okay, and since it involves a derivative, this the form of this or the effect of this boundary condition depends on the governing equation itself. Okay. So the ones we'll see most often in this class are going to be things like force, pressure, stress, bearing loads, things like that. Okay. And so just kind of be on the lookout for that. Okay? And just be aware that oftentimes when you're applying these, you have to specify direction as well. Okay. All right. And so unlike constraint type boundary conditions, you don't strictly need a load type boundary condition to run a simulation. I know ANSYS has an error message which kind of makes it seem like you need a load type boundary condition, but you technically don't. You can actually run a simulation with purely just constraint type boundary conditions. Okay. With that said, though, most of the time, unless you're doing kind of a test case, most of the time you are going to have a load type boundary condition. Just because that's just kind of naturally how we think about just how things interact with our physical system. Okay. But just know that there are situations where you can avoid having a load type. And so if you come across one of those situations where you're just applying constraints, don't worry about it. It's still going to run, even though I know that error messaging in ANSYS can be a little bit misleading in terms of that. Okay. Any questions on this so far? All right. And so when you're talking about load type boundary conditions, there's going to be a lot of options available to you. Okay? We took a brief look at these in our first two ANSYS activities. And so when you remember when we applied our boundary conditions, there was a long list of boundary conditions there, and the majority of those are load types. Okay. And so when you're choosing a load type boundary condition, it can be a little bit unclear sometimes, what exactly you should choose, or how exactly you should model a certain load. Okay. And actually, this kind of goes back to the question Ivan asked earlier today. When you're talking about load type boundary conditions, there's multiple different ones that you can apply to get the same result, right? And so we talked about force and pressure, right? And so you can apply a pressure boundary condition to give you the exact same result as a force, okay? And so that kind of begs the question, and people ask all the time, what's kind of the best way to apply load type boundary conditions if there's multiple options for them, if there's multiple ways that you can do it, okay? All right, so the kind of the advice that I give to people when you're applying load type boundary conditions is model it in a way, or apply it in a way that makes the most consistent physical sense with your situation. Okay, so a lot of times there's not that much of benefit, or there's not really a benefit of choosing a pressure versus a load in a situation. Where it is going to be beneficial is that if you have a physical situation and it makes more sense to you in your mind to apply it as a force, that's going to make a bigger difference than trying to compute, what's the equivalent pressure. So, when I put it like that, of course it seems obvious, yeah, duh, you should apply a load that is consistent with your physical situation, right? That's the whole point of FEA, right? And so, but I think, once you start getting into FEA, and, and I say this especially for this class, because, we're going to be doing more advanced stuff. I think it's very easy to get caught into kind of the game of FEA to say, okay? And so throughout this whole thing, I don't want you guys to forget, the whole reason we're running FEA is we're modeling a physical situation. Okay? So when you're making decisions in terms of how you're choosing the boundary conditions, how you're modeling those, what your equations are going to be, don't kind of lose track of the physical situation. Okay, so make sure that you're choosing things that are physically consistent. And so a good rule of thumb, or something that's good to know, is that if you are modeling a physical system and it has a load in the particular units, use those same units for your loads. Okay? And so, if you're doing an activity and a load is given to you in force units like newtons or pounds, use that for the load, right? Don't, of course you can convert that to a pressure or something and apply that pressure, but you're only just causing more work for yourself, and you're kind of opening yourself up to, making mistakes. Okay, so use the same units. Again, sounds very straightforward, but it's, you'd be kind of surprised. Okay. All right. All right, and so that's our two types of boundary conditions. So we have constraint type boundary conditions, and we have load types. Okay, so now that we have kind of a better understanding of what those two are and what effects they have on our solution, what I wanted to end with today is just some kind of practical considerations or practical advice that you can follow when you're applying your boundary conditions. Okay? Right, so number one. And so, we talk about boundary conditions and we talk about how they're an important part of the mathematical solution to the differential equation, right? With that said, you don't have to apply a boundary condition on every single surface, edge, point, on every single exterior point in your model. Okay? And so, yes, it's true. You need to have at least one constraint type boundary condition. More often than not, you're going to have at least one load type, probably more than one load type boundary condition in the model. Okay? But you don't need to, spend time to look for every single exterior surface in your model and apply boundary condition. Okay? Because what ANSYS does is that, for every surface that you don't apply a boundary condition to, it applies what's called a default boundary condition. Okay. So for structural simulations, the default boundary condition is called stress-free. And so what the stress-free condition basically states is that surface or that edge or whatever, that one is going to be exposed to air, basically. Okay, so there's basically going to be no external forcing. There's going to be no external kind of constraints that are being applied on that surface. Okay, so it's basically going to be no stress. Okay. It seems, again, it seems obvious if you don't really think about it. It's something that you probably won't ever think about. But just know that there is something there, and so you don't have to worry about applying a boundary condition at every single surface. Okay. Okay. And so when you're going to apply your boundary conditions, only really focus on the parts of your model that are being affected by some kind of external factor. Okay. And air does not count as an external factor most of the time. Okay. All right. Number two. For a 3D simulation in ANSYS or any software, you usually have a choice of, you can apply a boundary condition either on a surface, on a 2D surface, you can apply it on an edge, which is a line, or on a point. Okay. So a surface, of course, is 2D, an edge is 1D, and a point is 0D, I guess. Okay. All right. So generally speaking, the most preferable way is to apply your boundary condition on as wide or as large a surface or large an area as possible. Okay. And so what this means is that surface is often the most preferable. Okay, that's more preferable than an edge, which is more preferable than a point. Okay. That's not to say you can't apply boundary conditions on edges and points. And sometimes that's kind of what makes the most sense. But if you have the choice of either choosing a surface, an edge, or a point, generally you want to do the surface. Okay. And the reason for this, is that when you're applying boundary conditions, it's considered an edge effect. Okay. And oftentimes, if you have too big of an edge effect compared to some of the interior nodes or some of the surrounding elements, it can cause some mathematical irregularities. Okay. Right, question. With that said, for problem 8, with the face where the seat begins, where we apply the force there, yes, yeah. Yeah, so that's a good example. So, for problem 8 on the homework, you can either apply it on an edge or the surface. It would be better to apply it on that surface, yeah, where the seat begins. Mm-hmm. Okay. And you want to avoid those kind of irregularities as much as possible. Okay? I'll give you a very simple example. So let's say, let's say that you're modeling kind of a bowling ball rack. Okay, so you're at the bowling alley and you see a rack of bowling balls and they're all kind of lined up in a row. Okay, normally when you're applying the loads from all the bowling balls, you would distribute that load across the entire platform, right? But let's say instead that you took all the weight of the bowling balls and you applied it on a single point, right? That's basically the same thing as you taking a needle and then putting the weight of, whatever, 18 bowling balls onto that needle, okay? And so of course, that's gonna have a very different physical effect than if you kind of distribute that load all throughout. Okay? You're gonna have a needle that kind of pierces through, the rack, okay? And so you wanna avoid those situations. So, most of the time when you have a load, in a realistic situation, that load is applied, it's distributed across an area. And so you want to make sure that you kind of respect that in your simulation as well. Okay, and it leads to better mathematics too. Okay. All right. Number 3. All right. Technically, it's possible. You don't, you can apply more than one boundary condition at a surface, okay, or at the same location. And oftentimes that's appropriate, and that's kind of what's needed. Okay? And so, let's say that you have a situation. I'll take one from activity 3. Okay, and so for activity 3, we have basically we're going to be simulating a freeway signpost, right? And so you're driving on the freeway, you see those signposts that tell you missed your exit. Okay, and we're going to be modeling one of those. So those signposts, they're subjected to multiple forces, right? And so one force that it might be subjected to is wind pressure, right? So you have a wind that's blowing against the sign, that's causing a certain amount of force. Okay? At the same time, you may also have something that's weighing the sign down as well. Okay? And so you might have a situation where you're applying, 2 forces or 2 loads at the same location, and that's okay. Okay, and so it's not like I think sometimes when people are running FEA, they think when you apply a boundary condition on surface, that surface is opt forever. So that's not the case. You can apply multiple loads. Okay. What you do have to be careful of is that you don't apply both a constraint type boundary condition and a load type at the same location. Technically, you can, and ANSYS is not going to stop you from applying a constraint and a load type boundary condition at the same place. Okay, but it's going to be kind of a waste of space. Okay, because usually what happens is that when you apply a constraint type boundary condition and a load type boundary condition to the same place, the constraint type is usually going to override the load type boundary condition. So as an example, let's take our beam again. So on one hand, we have our pin support. The other side, we have our roller. Okay. And so here are constraint type boundary conditions on the left. And so it's where we have our pin support, right? If we try to apply a load here, okay, so we try to apply a force F, nothing's going to happen because we're going to push on this beam, but this beam is constrained to have a displacement of 0 on that side. Okay, and so we can push and push and push all we want. We can apply as much load as we want, but the constraint type boundary condition is always going to win. Okay, and so just kind of be careful of those situations of when you're applying your boundary conditions and you're not seeing a result that you want. You may want to check and see if you're applying a load type and constraint type at the same location. All right. Any questions on this so far? Can I repeat the example again? Sure. Yeah. So, for this example, we have a beam and we have a constraint type boundary condition on the left, right? And so this pin support right here, this is constraining. It constrains the displacement to be 0 on that side. And so if you try to apply a load onto that side, so you try to apply a force, then nothing's going to happen because there's going to be no deformation that occurs. You're only going to be pushing. It's basically like you're trying to push on like an immovable object. All right, and so the last piece of advice, or at least the last piece of practical kind of considerations that I'll give, it's something that seems obvious, and it's something I've already said today a couple of times. But when you're applying your boundary conditions, you want to choose the right boundary conditions that are physically consistent with your physical system. Okay. So again, I know it seems obvious, right? And so of course, you're not going to choose the wrong boundary condition. But the main reason why people kind of mess up their boundary condition, or the main mistake that people make, is actually because they don't choose boundary conditions that are consistent with their physical system. Okay? And so it's not an error that ANSYS is going to tell you about, right? And so if you choose the wrong boundary conditions, and so let's say you put the fixed support in the wrong location, or you put the force in the wrong direction, it's not something that ANSYS is going to tell you explicitly. Okay, it's a little bit different than the mesh, because if you have kind of a crappy mesh, sometimes ANSYS will tell you that your mesh is crappy. You need to remesh your model. Okay, the boundary conditions is something that's purely up to the engineer's discretion, right? So it's up to them to choose what are the most appropriate boundary conditions. Okay? ANSYS does some very basic checks just to make sure you have one constraint type boundary condition. You have some kind of action going on, but ANSYS really has no knowledge of the physical system that you're trying to model. ANSYS only really knows what the computer simulation is. Okay? And so when you're choosing your boundary conditions, just know that the correct selection of boundary conditions, that's on you as the engineer. And for the problems that we've been doing so far, and I would say this is kind of relatively true for most of the activities that we're doing. Okay. Of course, it's very obvious, what the boundary conditions should be because I give it to you in the activity basically. Okay. But in reality, a lot of times there's not going to be kind of a straightforward kind of decision that you have to make in terms of the boundary conditions. Okay. A lot of times you might have to make assumptions. Okay. Because when you run a simulation, ultimately you have to put a number, you have to put a direction on the boundary conditions. Okay, that's essentially what it kind of boils down to. But there's going to be some situations that don't really kind of lend itself well to that situation, right? And so if let's think of just a theoretical example. Let's say that you're running a simulation on a deep sea drilling rig, right? And so you have a drill, it's drilling underneath the ocean to find oil or whatever. Okay. And you want to make sure that the drill is not going to crack under all the pressure. Okay? One thing that you do know is that as the drill is drilling into the ground, okay, the ground is going to exert some kind of load onto the drill. Okay? But it's not going to do so in a uniform manner, right? And so it's going to be maybe more concentrated at the tip. Maybe it's going to be more concentrated at different parts of the drill head. Okay. But you don't have exact data on either. Okay? And so you're going to have to make some assumptions in terms of, as the drill is spinning, what's the most appropriate way to apply this force that's going to give you the most accurate results. Okay. And in that case, it's not clear. Do you concentrate more force at the tip, right? Or do you maybe concentrate more force on the part with the higher area? Okay, maybe it gets caught on a rock or something like that. Okay. And so, in practical situations, the decision is not going to be as straightforward as our activities. And so, that's kind of one thing I want to warn you about. Okay. So I'm going to try to factor this into the projects a bit. And so for the projects, I'm not going to tell you what the boundary conditions should be. I'm going to give you a part basically. And I'm going to tell you, here are some common situations that the part might be in. Okay. But at the end of the day, it's going to be up to you to choose, what are the boundary conditions that are most appropriate. And I want you to justify it too. Okay. So I want you to say, I'm choosing a force to put here. And these are my reasons for doing so. All right. Any final questions on this? Yeah.
Just to go back to your
yeah.
In terms of applying multiple boundary conditions, so for example, like something that came to mind was like a structural layer or fleet. At the same time, you're applying force. Is that something you can actually simulate at the same time?
Yep, you could. Yeah, so there's a module in ANSYS that does fatigue life analysis, and so you can factor that in. You can put in, this part has been through, such and such number of cycles, and then that can affect the structure of it as well. Yeah. Right, any other questions? This is just okay, all right, so that's all I have planned for today. So we'll end about 5 minutes early. And so on Wednesday, we'll pick it up again and we'll talk about material properties, which is, part 3 of kind of the basics of FEA. Okay. All right, so thank you guys for coming today. I know, this class is always late, so I appreciate you guys coming out or logging in. Okay, so hope you guys enjoy the rest of your evening, and I will see you on Wednesday.
Thank you, Dr. Chan.
Thanks, Ivan. Thanks, Ismail.
Professor,
Yep.
I just have one more question.
Sure. Yeah.
So in terms of real life scenarios, how do you like simulate non-uniform forces or loads?
Yeah, that's
over
a
a period of time?
Yeah. No, that's a great question. And it's a matter of kind of how complex that you want it to do. And so you'll see on our next activity next week is that you can apply a function. So you can say that a load is distributed according to this function. And so that's one way that you can do it. And so we're going to use that function to do a varying uniforms basically. But if it's more non-uniform than that, then you can apply basically different forces in different patches. You can define a certain patch here, maybe you apply a certain force there, maybe another patch here. So, there's a lot of detail that you can apply. It all kind of boils down to time in terms of how much time you have.
Because like the sign thingy comes to mind, like in terms of like the different seasons and the different wind directions and the different pressures.
Oh yeah.
How is that simulated? Like how is that random like movement or semi-random movement simulated or integrated into a simulation?
Yeah, no, that's a good question. So, when you have kind of random elements, you can run a stochastic simulation. And so what that means basically is that instead of kind of a set value for the force, you can sample it from a distribution. And so you can see that the wind direction has, magnitudes that change, has a certain average and it deviates by this much. The direction has a certain average and deviates by this much. And then what you do from there is that you run actually multiple simulations. And so you run, maybe hundreds of thousands of simulations. And then based with each one having kind of a random assortment of conditions. And then once you run the 1,000, then you take kind of the average, you kind of get the same statistics for the results. So you get like a mean, the standard deviation for the results.
Oh, I see. Okay.
Yeah.
Cool. Thank you.
Yeah.
Yes, sir.
Thanks, you too. Hey.
So I'm doing my graduate project. I wanted to ask if you'd be on the 3 professors on my board.
Yeah, I mean, I appreciate you asking really early. And so sometimes you get asked, like, can you be on the meeting tomorrow? I'm like, send me. Do you have kind of like an abstract of kind of what you're working on?
Yeah, so I started it last semester, and so this semester is a continuation.
Okay.
I can send you the syllabus I have for the class.
Sure. Yeah, that'd be great. Yeah. So yeah, I mean, the reason I asked, most of the time, if it's at least partially related to what I do, I'm always happy to do so. But I want to make sure that I have enough knowledge that I can get feedback. So,
yeah.
Yeah. Once you send me your abstract and kind of the syllabus, and then yeah, I mean, if it's within my wheelhouse and I know about enough, I'd be happy. So
Yeah, I'm doing a thermal simulation on a battery pack.
Okay.
And so I'm using ANSYS inside.
Oh, perfect. Yeah, I'd be happy to. I'd be happy to help.
Awesome. Thank you so much.
Who's your advisor?
Dr. Wang.
Okay, Dr. Oh, okay. Yeah. Okay. Yeah, sounds great.
Awesome.
And what was your name?
Mariah.
Mariah. Okay. I think I know you've been in my class before, but yeah.
Yeah, so it's been online.
Yeah,
so it's like
online.
the
So
face-to-face.
yeah. So
For
so
sure.
kind of case some people. So, yeah, I'd be happy.
Awesome. Great. Thank you so much.
Yeah. Yeah. Have a good evening.
You too.
Monica, why don't you send me what you have? Why don't you email me your code right now, and then I can probably give you better feedback on that. Yep.
Okay, sounds good. Thank you.
Yep.
Bye.
Right. Bye, Monica.